NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn how every real number can be split into an integer part and a fractional part, and how that connects to the floor function. We'll visualize the idea on number lines and do two examples, one positive and one negative. Here is the key statement. For any real number x, there exists an integer n and a decimal part p with 0 less than or equal to p and p strictly less than 1, such that x equals n plus p. We give names to these two pieces. The integer part, n, is called the floor of x, and we write floor of x using the left and right floor brackets. The decimal part p is called the fractional part of x, and we write curly braces. Combining these, x equals floor of x plus fractional part of x. We will exactly follow the given algorithm to split a real number into its integer part and its fractional part. Problem: write the real number x equals 2.5 as one integer part and one fractional part. Step 1. We state the number. X equals 2.5. Step 2. Decompose x into an integer and a decimal part. So x equals 2 plus 0.5. Step 3. Evaluate the floor, also called the integer part. The floor of 2.5 equals 2. 2 is an integer. Step 4. Evaluate the fractional part. The fractional part of 2.5 equals 0.5, which lies between 0 inclusive and 1 exclusive. Finally, verify the identity. X equals the integer part plus the fractional part. That is 2 plus 0.5. In this example, we will decompose a decimal number into its integer part and its fractional part. Here is our example. The word example appears. Now the problem statement. Write the following real number as an integer part and a decimal part. X equals 9.57. Step 1. Decompose the number. We draw a number line from 9 to 10 and place the point x at 9.57. Visually, starting at 9 and moving 0.57 gives x, so we can write x equals 9 plus 0.57. Step 2. Find the integer part. The floor of a number is the greatest integer less than or equal to the number. Therefore, bracket x equals bracket 9.57 equals 9, and 9 is an integer. Step 3. Find the fractional part. The fractional part is the amount after removing the integer part, and it always lies between 0 inclusive and 1 exclusive. Thus, curly brace x equals curly brace 9.57 equals 0.57, and 0 is less than or equal to 0.57, which is less than 1. Finally, confirm the decomposition. We return to the number line picture and write the identity x equals bracket x plus curly brace x equals 9 plus 0.57, which equals 9.57. Summary: we decomposed x equals 9.57 into its integer part and its fractional part. The integer part is 9, and the fractional part is 0.57, with the check that 0 is less than or equal to the fractional part, which is less than 1. Final answer: the integer part is 9, and the fractional part is 0.57. We start with the word example. The problem states x equals 1/2. Step 1. Use the decomposition identity. Any real number x can be written as the floor of x plus the fractional part of x. Since x equals 1/2, we can write x as 0 plus 1/2, separating the integer part from the leftover fraction. Step 2. Determine the integer part, the floor. The floor of x is the greatest integer less than or equal to x. For x equal to 1/2, the greatest integer not exceeding 0.5 is 0. Step 3. Determine the fractional part. The fractional part equals x minus the floor of x, and always lies between 0 inclusive and 1 exclusive. Substituting x equals 1/2 and floor x equals 0, we get the fractional part equals 1/2, which indeed lies between 0 and 1. Step 4. Verify the identity with our values. Replace floor x by 0 and the fractional part by 1/2. We used the decomposition identity x equals floor x plus fractional part. The floor of 1/2 is 0. The fractional part of 1/2 is 1/2. Together they reconstruct x exactly. In this short lesson, we will decompose a negative number into its integer part, also called the floor, and its fractional part. The example is x equals negative 6.25. Here is the example. Under it, we will place the number to decompose. X equals negative 6.25, shown in bright orange. Step 1. Use the decomposition rule. Any real number x can be written as x equals floor of x plus fractional part of x. For negative 6.25, the greatest integer less than or equal to it is negative 7, so we can write x equals negative 7 plus 0.75. To visualize why the floor is negative 7, look at the number line. Negative 6.25 sits between negative 7 and negative 6. The floor is the greatest integer not exceeding the point, which is negative 7. Step 2. State the floor explicitly using its definition. The floor of x is the maximum integer, n, such that n is less than or equal to x. Therefore, the floor of negative 6.25 equals negative 7, an integer. Step 3. Compute the fractional part. By definition, fractional part of x equals x minus floor of x. Using x equals negative 6.25 and floor equals negative 7, we get fractional part equals 0.75. Notice it lies in the interval from 0 inclusive to 1 exclusive. Quick check. Adding the floor and fractional part gives negative 7 plus 0.75, which equals negative 6.25, our original x. So the decomposition is complete. Floor of x equals negative 7, fractional part of x equals 0.75. In this lesson, we will decompose a negative irrational number into its integer part and its fractional part using floor and fractional part definitions. Here is our example. We will express the real number x equals negative square root of 2 as the sum of an integer part and a fractional part. Step 1. We first note a helpful decimal approximation to guide our intuition. Square root of 2 is about 1.414, so x is about negative 1.414. Many solutions write x is approximately negative 1.4, which is about negative 2 plus 0.6. However, for an exact decomposition, we will later replace 0.6 by 2 minus square root of 2. Step 2. We compute the integer part using the floor function. The floor of a number is the greatest integer less than or equal to that number. Since negative 2 is less than or equal to negative square root of 2, which is greater than negative 1, the floor is negative 2. And yes, negative 2 is an integer. Step 3. Now, the fractional part. It is defined as x minus its floor, and always lies between 0 and 1. Substituting the values gives fractional part of x equals negative square root of 2 minus negative 2, which simplifies to 2 minus square root of 2. Numerically, that is about 0.5858, satisfying 0 less than or equal to the fractional part, and less than 1. Here is our example. The word example appears, followed by the system of equations exactly as given. Before we start, recall the key rule for the floor function. If the floor of k equals n, then n is an integer, and n is less than or equal to k, and k is less than n plus 1. Step 1. Multiply the first equation by negative 3 and the second equation by 2 to eliminate the floor of x. Step 2. Distribute to simplify each equation. Step 3. Add the two equations together. The negative 6 floor of x and the positive 6 floor of x cancel. We get negative 11 floor of y equals negative 22. Step 4. Divide both sides by negative 11 to get floor of y equals 2. Step 5. Substitute the value floor of y equals 2 into the original second equation. 3 times floor of x minus 2 equals 1. So 3 times floor of x equals 3. Therefore floor of x equals 1. Finally, translate these floor values into ranges for x and y using the rule. If the floor of x equals 1, then x is between 1 inclusive and 2 exclusive. If the floor of y equals 2, then y is between 2 inclusive and 3 exclusive. Therefore, our final answer is floor of x equals 1 and floor of y equals 2, with the ranges 1 less than or equal to x less than 2 and 2 less than or equal to y less than 3. In this lesson, we solve a system involving floor brackets. We will follow a clear 4-step structure. Interpret the brackets, simplify, solve, and verify. Here is the given system. The square brackets denote the floor function. Step 1 will use the key rule that the floor of an integer equals the integer itself. Because the left sides are floors, they are integers. So The right sides must also be integers. This forces x and y to be integers. Once we know that we can remove the brackets safely, now remove the brackets and simplify both equations into standard linear form. We solve by elimination. Subtract the first equation from the second to eliminate y. Finally, we verify the integers in the original floor equations. Conclusion: because the floor outputs integers, the right sides must be integers, forcing x and y to be integers. Removing the brackets yields a simple linear system. Removing the brackets yields a simple linear system. Solving by elimination gives x equals 4 and y equals 5. Both values satisfy the original floor equations. Here is the system. Notice that the left sides are floor expressions, which are always integers. Key idea: because both left-hand sides are integers, for the equalities to hold, the right-hand sides must also be integers. So 5 minus x is an integer, which forces x to be an integer. Likewise, negative x minus y plus 6 is an integer. With x already an integer, that forces y to be an integer as well. Because x and y are integers, each floor expression becomes the value itself, so we can remove the brackets. This gives an equivalent pair of linear equations. Now, rearrange both equations to collect x and y on the left and constants on the right. From the first equation, we get 2x plus y equals 7. From the second equation, we get 2x plus y equals 3. These two lines have the same left-hand side but different constants. That means they are parallel lines in the xy plane and never meet. Let's quickly visualize them. Therefore, the system is inconsistent and has no solution. Algebraically, if 2x plus y equals 7 and also equals 3, then 7 would equal 3, which is impossible. So the system has no solution. Summary: because the floor expressions force the right-hand sides to be integers, x and y must be integers. Removing the brackets yields two parallel lines, so there is no solution. Two parallel lines, so there is no solution. In this example, we will use the floor function rules to connect two bracketed expressions and compute the value of another one. We are given the condition bracket 2 times open x squared plus 1 close bracket equals bracket 4x bracket. Our goal is to evaluate bracket open x plus 1 close squared bracket. Set this common floor value equal to the integer n. So bracket 2 times x squared plus 1 bracket equals bracket 4 x bracket equals n. We will repeatedly use the definition of the floor function. Bracket y bracket equals n if and only if n is less than or equal to y and strictly less than n plus 1. Applying the definition to each floor, we get a system. N is less than or equal to 2 times x squared plus 1, and strictly less than n plus 1. And also n is less than or equal to 4x, and strictly less than n plus 1. Now add the left sides, the middles, and the right sides of the two inequalities. This yields 2n is less than or equal to 2 times x squared plus 1 plus 4x, and strictly less than 2n plus 2. Distribute, and then complete the square inside the middle expression. Divide the entire double inequality by 2. We obtain n is less than or equal to open x plus 1 close squared and strictly less than n plus 1. By the floor definition again, this means the floor of open x plus 1 close squared equals n. But n was the common value, and it equals bracket 4x bracket. Therefore, the floor of open x plus 1 close squared equals bracket 4x bracket. Recap. Start with the common integer value n, convert floors to double inequalities, add them, complete the square, divide by 2, and use the floor definition to conclude. Final answer. The floor of open x plus 1 closed squared equals the floor of 4x, equals the floor of 4x. Example. We will find the integer part, or floor, of the quantity open parenthesis 1 plus square root of 2 close parenthesis raised to the 6th power. Here is the key relation we will use. The sum open parenthesis 1 plus square root of 2 close parenthesis to the 6th plus open parenthesis 1 minus square root of 2 close parenthesis to the 6th equals 198. Our goal is the floor of the first term. Why is that sum an integer? For the sequence a sub n equals open parenthesis 1 plus root 2 close parenthesis to the n plus open parenthesis 1 minus root 2 close parenthesis to the n, you can show the recurrence a sub n plus 2 equals 2 a sub n plus 1 plus a sub n, with a sub 0 equals 2 and a sub 1 equals 2. Marching forward gives a sub 2 equals 6, a sub 3 equals 14, a sub 4 equals 34, a sub 5 equals 82, and finally a sub 6 equals 198. From the identity, we can isolate the first term, open parenthesis 1 plus root 2 close parenthesis to the sixth equals 198 minus open parenthesis 1 minus root 2 close parenthesis to the sixth. Now, note that the absolute value of 1 minus root 2 is less than 1. Raising it to the sixth power makes a very small positive number, strictly between 0 and 1. First, look at the negative of that tiny number. It lies strictly between -1 and 0. Therefore, the floor of negative open parenthesis 1 minus root 2 close parenthesis to the sixth equals -1. Next, subtract the same tiny positive number from 198. That puts our values strictly between 197 and 198. Hence, the floor must be 197. As a quick check, 1 plus root 2 is about 2.414. Raising to the sixth power gives roughly 197.99, which is consistent with a floor of 197. And the exact integer, 198, came from the Pell-type sequence a sub n. Final answer, the floor of open parenthesis 1 plus root 2 close parenthesis to the sixth is 197. In this lesson, we solve a nested radical problem and determine the floor, that is the greatest integer, less than or equal to each term. We are given a sub-north equal to the square root of 1,366 plus the square root of 1,366 plus dots, with 1,366 repeated n times. A clean way to work with a nested root is to define a recursion. Let a 1 equal square root of 1,366, and for n, at least 2 define a sub-north equal square root of 1,366 plus a sub n minus 1. Squaring gives a sub n squared equals a sub n minus 1 plus 1,366. Now compute the first term. Since a 1 equals the square root of 1,366, its value is approximately 36.95. So 36 is less than a 1, and a 1 is less than 37. Consider n equals 2. From the squared relation, we have a 2 squared equals a 1 plus 1,366. Substitute the approximation for a 1 to get a 2 squared approximately equal to 36.95 plus 1,366, which is 1,402.95. Taking the square root gives a 2 about 37.45. Hence 37 is less than a 2 and a 2 is less than 38. Next, n equals 3. We again use a 3 squared equals a 2 plus 1,366. Using a 2 about 37.45, we get a 3 squared about 37.45 plus 1,366, which is 1,403.45. So a 3 is about 37.46. And therefore 37 is less than a 3, and a 3 is less than 38. In general, for n equal k, we have the same squared relation. ak squared equals ak minus 1 plus 1,366. The numerical evidence shows each term after the first lies strictly between 37 and 38. So we record 37 less than ak less than 38. Therefore, the integer part of a 1 is 36, and for all n greater than 1, the integer part is 37. As a quick intuition, if the sequence approaches a limit L, then L equals the square root of 1,366 plus L, which solves to about 37.45. That sits between 37 and 38, matching our bounds. Final result confirmed. The floor of a n equals 36 for n equals 1, and 37 for every n greater than 1, and 37 for every n greater than 1. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.